Hello, Fargo Moorhead Robotics team. Today I wanted to talk a little bit about something called Slew Rate Limiter and then a PID controller. So with the robot chassis, when you use the Xbox joystick and you push it all the way forward, you're basically doing kind of a full bang bang control. So you're going from zero to fully commanded movement. And that motor controller will be more than happy to take that motor from a dead standstill to as fast as it can go, as fast as possible. And that can be really, really hard on the motor, the gearbox, the chain, everything. So one of the things that we can do to limit that is use something called a slew rate limiter. So here is an example where we have an input that just goes from zero motor position or speed to maximum motor speed. And that motor is going to do everything it can to drive that fast. Well, in the WPILib, there's a class called the Slew Rate Limiter. And so we're using this right now in the robot chassis. And so what this does is it just limits the maximum rate of change over a time period. And this is all controlled in the configuration file. There's a Slew Rate Limiter setting for the forward-back motion of the robot and the right-to-left motion of the robot. And so this is the graph that this is what it looks like. So when you command 0 to full speed ahead, it's going to limit that rate of change over a period of time. And so the way we can change that is we have this forward back slew rate and right left slew rate. So right now we have, and the larger numbers mean faster response time. So we have the forward back response faster than the left to right response. So the next thing I wanted to talk about is a PID controller. I think this year this is going to be a very important thing to understand and program into the robot, since both robots are going to have an elevator and a rotation mechanism of some sorts. We're going to need to be able to keep that from like drifting over time, right? So if we lift the arm to a certain position, we really want that arm to stay there. And so a PID controller is something that can do that. And so this is a diagram of a PID controller. It looks really complicated, but it's really simple. You have some sort of set point. Let's just think about it with the robots, that we have an arm that we want to move to a certain position, and we really just want it to stay there. So we have encoder positions. The motors have encoders in them that can tell us the position is 15 rotations of the motor. And you can change that. So if you look at the drive subsystem, I have it set so that when we get the position from the encoders, we're actually getting distance in meters. And we can do the same thing with the robot arm. We can get the rotation in rotations or radians or degrees or whatever the heck you want. But anyways, so let's say our arms are sitting on the ground. If you saw that video that we posted a couple days ago on Gilded, that's the Fargo's robot arms moving to roughly horizontal and then using a PID controller to keep it there. So let's say the position of the arm is 0 and we want to move it to a value of 10. So what'll happen is we'll take that set point of 10 and the current position of 0, and we'll subtract the two and we'll get this error. So we'll see that the error is a large error of 10, and that's that E of t. Well, then what we do is we multiply that error by some sort of proportional constant, Kp. So all we're doing here is we're taking our error, we're multiplying it by this constant, and we're feeding it into a summation. Then the I part of the PID controller is the integral. So an integral, if you've had calculus, it's just taking the area under the curve. So if you plot like if you graph some sort of equation, the integral is just the area under that curve. And another way of thinking of it is you can just like integrate the error over time, right? So if the error is 10, then the integral at that time step is 10. If you come through this loop and do it a second time, well, if the error is still 10, well, now you're going to take 10 plus 10. Now you have an error of 20. And as that error continues to build, that number gets larger and larger. So then you multiply that integral, that addition, that summation, with the Ki constant. And then you feed that to the summation block here. And then the final thing you have is the derivative. So once again, if you've had calculus, the derivative is just the difference of an equation, but in time domain steps, you can think of it as just what's the difference between my last sample. So once again, if the error was 10 this time, and we come through and the error is still 10, well, the difference in that error is 0, right? And so that's one way of thinking of it. So if you get this difference, you can then multiply it by your differential or derivative constant, KD. So all three of these elements go to a summation. You sum them all, you add them all together, and that becomes your output to your plant or process. So in the case of the robot arm, the R of t is the desired position of the arm. The Y of t is the current position of the arm. E of t is the error between the desired position and the current position. You then multiply through the PID gains, and you get U of t. And U of t is actually the desired motor speed, right? So we're controlling the motor speed. And then that goes into the system, the robot, and ultimately gets a new position. And I tried to do some simulations here, and this really isn't working. So what really is nice is just looking at the motor, the data that we plotted from the robot. So this is the actual data from the robot on the video that's posted on Gilded. So what we start out with is here we have the ARM encoder in this, I don't know what you call yellow color. And so the encoder starts out at 0, meaning it's sitting on the ground. And the error then, so this is the error between the desired position and the actual position. And I thought we set it to like -6, or I thought it was -8. Must be -6. And so then what happens is as soon as we start running this thing, we see that there's an error. Yeah, there's some error. So this is showing us that the error is like -4. So then it starts to drive the motor in a certain direction, and we can see that the encoder is now telling us that we're getting closer and closer to that 6, and we can see that the error is decreasing. At a certain point in time, it overshoots the set point, and the error never actually goes to 0. And so this was running only a proportional controller. So then when you get the integral in there, the integral will try to close this loop and get rid of the this kind of offset between the current set point and where you want it to be. So anyways, that's a PID controller. I think I'll do another video here later that I'll walk through what we've got going for the Fargo robot code. So stay tuned. Thanks everybody.